This illustration is about the finite difference method for linear boundary value problem, and we will discuss here the iterative solution strategy. The same methodology will be extended while solving the elliptic partial differential equations. So here we have a problem d2y dx squared equal to 100y. It's a simple two-point boundary value problem, where we have boundary conditions y of 0 equal to 1 and y of 1 equal to e raised to the power minus 10. We have the exact solution available, y of x equal to 10, e raised to the power 10x. It should be e raised to the power minus 10x. Okay. So let's develop the scheme. While solving the differential equations using finite difference scheme, we have to provide the equivalent, numerical equivalent for the derivatives and for all the nodal points. So for second derivative, we have the expression yi plus 1 minus 2yi plus yi minus 1 minus h squared by 6 f fourth prime of xi. While solving the equation, we only limit our expressions to the three terms. We do not include the error term. This is important for theoretical studies for the problem. So for this problem, we have the finite difference form as yi minus 1 minus 2 plus 100 h squared times yi plus 1. So this equation should be applied for all of the interior points where we want to calculate the values. However, if we write this equation in iterative fashion, so we may come across this simple expression by I at k plus first iteration. This can be computed by using the values of yi minus 1 at the kth iteration and yi plus 1 at the kth iteration, divided by 2 plus 100 h squared. So let's solve this problem. So I generate the x values. Okay, let's size 40. Okay, x values. So from 0 with a step size of 0.1 plus 0.1. Okay, so this is the domain of x values. Let me develop here the exact solution y of x. This is for comparison. So this is equal to e raised to the power minus 10 times the x value. So we can generate these values. Now let's go for the numerical approximation. So I call it y computed. So for this solution, we have the boundary values available, y of 0 equal to 1. So this point, so this value is available equal to 1. And we have the other value available at the end point, y of 1 equal to e raised to the power minus 10, minus 10x. So let's generate this value. It is e raised to the power minus 10. Okay. So we have the boundary values, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 uh, interior points at which we have to write the finite difference equation, and then we can proceed. So we have to solve a 9 by 9 metric system that can be generated. The other strategy is to solve by using the iterative scheme. So that begins with the guess value. So for example, if we like to see the graph of this y of x, so it's a kind of decreasing function. So let me select a value as 1 minus x. It's a decreasing straight line. So I have taken some guess values for the solution. So these are the guess values. At the iteration number, I would say this is the values, iteration value 0 and yc1 at first iteration. Let me see whether it works or not. So we will generate several iterations. So this has not been generated. Okay, we can manually generate those things. Okay, so for all iterations, the first value will remain fixed. So for several iterations, this will remain fixed, and this should also remain fixed. Okay, now let's generate the solution. We have assumed a guessed solution, and now we can program this equation over here. So yi value, so at the ith node, the value will come from the values available for yi minus 1, which is over here this value, and then yi plus 1. So let's write this expression here. So it is equal to a value yi minus 1, previous value, plus, sorry, this is for yi plus 1. Let's write that in inconsistent fashion. It is equal to yi minus 1 plus yi plus 1 at the previous iteration, and divided by 2 plus 100 times h squared. H is 0.1 and it's squared. So we will generate a new value of yi. The same will be done for all of the values, for all of the points, and then we can proceed for further iterations, since the iterative methods should be continued so that we have a converged solution. So in Microsoft Excel, on similar lines, if you want to extend or continue iterations, you have to accordingly drag the solution domain, and that will generate the solution. So let's plot, let's see whether the solution has converged up to these many iterations. So I will plot. Select data. The first series x values, and then the y values. Let's first select the exact values. So exact solution, it has appeared. This should be the y of x. The next series should be, I would say, it is the y computed at the 0th iteration, x values, and then y values for the first, it is the starting initial guess value. So it is the straight line, and let me add a new series after several iterations. How many? 1 2 1 2 3 4 5 6 7 8 9 10 11. So this is YC at the 11th iteration. Again, some x values, same x values, and for the solution, I will take the solution values at this point. Okay, so we have found a green curve which is very close to the real solution. So that's the way we can work out the solution of boundary value problem, linear boundary value problem, and we have used the iterative technique. This technique is similar to the Jacobi method that we discussed. So the solution has converged from red line to the green line, uh, which is the very close to the exact solution represented by the blue line.